The following video, along with my bird, is just a briefish introduction into dimensions. So there's a few videos that we're gonna run, and wouldn't you know it, that will lead us into the basics of the underlying information that is required to be understood in order to understand exactly what chaos theory is. Chaos theory is used in Shut up! Fucking bird. It's used in microbiology, DNA sequencing. It's used in life studies, prey-predator applications, that sort of thing. I had a few formulas dug out somewhere regarding the predator-prey formula. I don't know, I stuck it up there or something. It's a piece of paper. Is this it? What's this? This might... this is something else. But anyway, in order to draw a good, accurate representation of a chaos formula, you have to be able to do it in such a way that it's correct. Now, if you just take real data and you project it onto a flat screen, the problem with that is that the calculations that are involved are they're too complicated, and I don't know why that just happened, but there, okay. So what you do is you take the real numbers and you put them into a coordinate system. Then you have to translate that coordinate system so that it matches how the pixels are drawn on a computer. Then you have to do some scaling in order for the pictures to look right. Now, what's interesting about some of these chaos formulas is that the one-dimensional, or rather the two-dimensional, actually it's a one-dimensional formula called a logistics formula, which we're going to get into here very shortly. It looks like it's two dimensions, and some of the two-dimensional chaos formulas look like they're three-dimensional images if you kind of look at them. What I didn't know was that the logistics formula is actually part of what's called the Mandelbrot Set. It's like the middle line of the Mandelbrot Set. And then there's another formula called the Julia Set, which theoretically is the formula for the outline of the Mandelbrot Set. All of this stuff I just figured out like a couple of weeks ago. And trying to do a video about this stuff, in layman's terms, it's complicated. And I'm going to try to do that at the end of the stream. I'm going to try to pull some of this stuff together, and so that people without any mathematical sense can make sense of it. And the question that I have is, what exactly is the dimension between the fractal dimension, and does that relate to fractional dimensions? In other words, if you draw a picture of a square, it's in a plane, and that plane represents two dimensions. It has an x and a y. And then if you draw a cube, it's three dimensions. Now, when I was looking at what's called the Sipinski Triangle, which is what we're going to get into, the first triangle is completely solid. The second one, there's parts missing, and they came up, there's this equation that relates to the number of copies equaling the magnification. I don't really understand how they came up with that formula, but that's the formula that's used in order to calculate the dimension of that particular self-similar reproducing life. Well, it's actually called automata. It's like representing life forms in computer programs and that sort of thing. There's some ways to do that. But the real question is, if you have, let's say, an electronic circuit, and it has that electronic circuit has what's called a feedback loop. In that feedback loop, it may have like a resistor and a capacitor in there, and it filters out a signal. So if you got this signal coming in, and it's got a bunch of noise, and it's got some information on it, you run that into your filtering network, and that filter has a certain formula. And what it does is it filters out the noise so that you can get the information or the data that's coming in on the signal. If you crank up the feedback too much, you get what's called it's the term is actually called feedback. Like if you put a microphone next to a speaker, you hear this high-pitched sound. You can also take a videotape recorder and connect the camera to the TV, face it to the TV, and then you can blow up I've blown up a few VCRs that way, literally, because the signal was feeding back so much that it overheated the transistors. So you have to be careful when you're doing that with video. You have to kind of do it off to the edge. And so a fellow that I met quite a while ago was studying what's called instrumental transcommunication, and he was using video feedback looping as a means of peering into some dimension and seeing these pictures of there's like landscapes, there's people. They don't seem to be moving around, but they're just like these static pictures. So I'm asking myself, it's not this isn't like the fourth and fifth dimension. This has to be some dimension that's in between dimensions. I'm just just throwing this stuff out there. And but in order to get to that point, you have to understand some of the basics that goes into all of this stuff. Now, this guy that does this video, he took this information from a book. Well, I'm assuming. And there was some other video of this guy that did this video by the name of, the name on the YouTube is Veritasium. And somebody else, I guess, was complaining, saying that this Veritasium fellow was taking all the credit by putting all this stuff together, when this information's been known for like 20 or 30 years already. That's really not the point. The point is, I thought he put together the video to a point where me as an exploratory chaos theory person, it showed something that I'd never seen before, which it adds more information to making the looks of the chaos formula, making it the next higher dimension. It's kind of hard to explain, but when you see some of these formulas, there's one called it's like the butterfly effect or something, and it's got like there's a bunch of things going on, and if you take that formula and you use certain aspects of that formula and apply it to your Cartesian graph and that sort of thing, you see different pictures. And my eventual goal is to create a hologram of what's being done here, and these are not actual three-dimensional pictures. But they're holograms, which is supposedly a three-dimensional representation. But what if you could take something that's in between dimensions? How can you represent that? So we're going to watch this anyway. I'm going to go back to the Sipinski Triangle thing, and we're going to go through that first. And let's see if I can find the right one here. Let's watch this video, and I'll bring this up here, and I'll talk about it for a minute, I guess. If I can find the right thing here. Should be... Actually, no, we're going to have to... We'll watch this other one first. We'll just do this one, and we'll talk about it.
What's the connection between a dripping faucet, the
Mandelbrot
Set,
by
a population of rabbits,
on
thermal
YouTube.
convection in a fluid, and the firing of neurons in your brain?
And that would be the wrong
it's
picture.
This one simple equation.
I think I
This video is sponsored by Fast Hosts, who are offering UK viewers the chance to win a trip to South by Southwest if they can answer my question at the end of this video. So stay tuned for that.
Well, we're not really interested in that, but anyway.
So it goes from 0 to 1. And
Right,
as it
this is
approaches
the
that
logistics
maximum,
equation.
then this term goes to 0. And
basically what all this means is that you're taking a bunch of numbers, and those numbers you're coming up, you're iterating, or you're increasing this x number, and then that result is added to the next x number, and you take the next x number and put it back into the equation. So you would think that these numbers, it would just blow up into infinity, but the fact is that there are some instances where this doesn't happen. In other words, let's watch this guy.
that constrains the population. So this is the logistic map. xn plus 1 is the population next year, and xn is the population this year. And if you graph the population next year versus the population this year, you see it is just an inverted parabola. It's the simplest equation you can make that has a negative feedback loop. The bigger the population gets over here, the smaller it'll be the following year. So let's try an example. Let's say we're dealing with a particularly active group of rabbits. So r equals 2.6. And then let's pick a starting population of 40% of the maximum, so 0.4. And then times 1 minus 0.4. And we get...
No, I'm not saying that he knows what he's talking about, but he did do a good job with the video.
In the first year. But what we're really interested in is the long-term behavior of this population. So we can put this population back into the equation. And to speed things up, you can actually type 2.6 times answer times 1 minus answer. And what you see is the first few years change, but the equilibrium population remains the same. So we can basically ignore the initial population. So what I'm really interested in is how does this equilibrium population vary depending on r, the growth rate? Well, as you can see, if I lower the growth rate, the equilibrium population decreases. That makes sense. And in fact, if r goes below 1, well then the population drops and eventually goes extinct. So what I want to do is make another graph where on the x-axis I have r, the growth rate, and on the y-axis I'm plotting the equilibrium population, the population you get after many, many, many generations. Okay, for low values of r, we see the populations always go extinct, so the equilibrium value is 0. But once r hits 1, the population stabilizes onto a constant value, and the higher r is, the higher the equilibrium population. So far, so good. But now comes the weird part. Once r passes 3, the graph splits in 2. Why? What's happening? Well, no matter how many times you iterate the equation, it never settles onto a single constant value. Instead, it oscillates back and forth between two values.
Now, actually, what this is called, This was termed when they first got into all of these discoveries. This is called the doubling route to chaos.
One year the population is higher, the next year lower, and then the cycle repeats. The cyclic nature of populations is observed in nature too. One year there might be more rabbits, and then fewer the next year, and more again the year after. As R continues to increase, the fork spreads apart, and then each one splits again. Now, instead of oscillating back and forth between two values, populations go through a 4-year cycle before repeating. Since the length of the cycle or period has doubled, these are known as period doubling bifurcations. And as R increases further, there are more period doubling bifurcations. They come faster and faster, leading to cycles of 8, 16, 32, 64, and then at R equals 3.5.
All right, so he comes up with a particular number, which is called the Feigenbaum constant, which I'm not going to quite get into yet. But if you noticed this doubling route to chaos, there's what's called self-similarity, which I was talking about regarding this Sipinski Triangle, which we're going to get into in a minute. But if you look at this, I'm thinking to myself, well, it's going to go into, the numbers are just going to go crazy here, and there's no self-similarity. I don't know exactly how that relates to this particular setup, but it's there at the beginning, and the reason for this is there's what's called when you run these programs on the computer, you have to do what are called iterations, and you do something like 1,000 or 5,000 iterations. And nothing happens during that phase of the program. And so what you're looking for is either the iterations go off to infinity, or they center around certain numbers. Like in this case, it's actually centering around a certain number called the Feigenbaum. Well, actually, no, I don't. What is that number? Yeah, I'm not going to say that yet because I could be saying something wrong. But there is a number that this settles on. And what I wanted to try to explain is that there's different situations and different maps, different equations, where the numbers each iteration may jump back and forth between different numbers. It might be like 3 different numbers or 10 different numbers. Or it may center around what's called certain points. And when the entire graph centers around certain points, those are what are called strange attractors. And that's also part of chaos theory, which is more advanced. So let's watch this.
5.7, chaos. The population never settles down at all. It bounces around as if at random. In fact, this equation provided one of the first methods of generating random numbers on computers. It was a way to get something unpredictable from a deterministic machine. There is no pattern here, no repeating. Of course, if you did know the exact initial conditions, you could calculate the values exactly. So they are considered only pseudo-random numbers. Now you might...
And this is another thing. They're saying that you can never know what the initial conditions are if you jump into the middle of an equation and its process. You don't know the initial conditions. That's just a thing. Don't ask me about it because I haven't a clue.
Expect the equation to be chaotic from here on out, but as R increases, order returns. There are these windows of stable periodic behavior amid the chaos. For example, at R equals 3.83, there is a stable cycle with a period of 3 years. And as R continues to increase, it splits into 6, 12, 24, and so on before returning to chaos. In fact, this one equation contains periods of every length. 37, 51, 1052, whatever you like if you just have the right value of r. Looking at this bifurcation diagram, you may notice that it looks like a fractal. The large-scale features look to be repeated on smaller and smaller scales.
Now here we're talking about self-similarity. We're talking about automata. That's a term that computer programmers use with what's called life. It's called, shut up, bird. And that goes on to the Sipinski Triangle, which is what I'm going to get into in a minute.
And sure enough, if you zoom in, you see that it is, in fact, a fractal. Arguably the most famous fractal is the Mandelbrot Set. The plot twist here...
Now, this is where I didn't know. There's some information that I didn't know about. So if you look at the edges, if you look at the outside edges, and you zoom in on the outside edges, there's what's called a lot of self-similarity. There's the Mandelbrot set repeats itself into infinity. So like you're zooming in. Well, this is a two-dimensional picture, minus this gray stuff over here. But watch what happens when the center line of this Mandelbrot set, if you rotate it in such a way, it turns out to be this logistic equation. Well, the logistic equation is a one-dimensional equation. And this is a two-dimensional object, and yet he's rotating it into a three-dimensional object. Watch this.
Is that the bifurcation diagram is actually part of the Mandelbrot set. How does that work? Well, quick recap on the...
So you can see, now it looks like it got reversed here, but let's just do this again. Maybe I can... You can see here there's definitely three dimensions happening. Hang on just a minute here. I can't really stop it now.
And you see that it is, in fact, a fractal. Arguably the most famous fractal is the Mandelbrot set. The plot twist here...
So again, the logistic equation is in the center of this Mandelbrot set, but...
Here is that the bifurcation diagram is actually part.
It still looks two-dimensional in a way, but it isn't.
Of the Mandelbrot set.
It's actually... That's a three-dimensional image. It looks that way. I mean, I could be wrong. It's just a question.
How does that work? Well, quick recap on the Mandelbrot set. It is based on this iterated equation.
All right, so z n plus 1, what that means is that's the next, like you do zn squared plus c, you come up with the number. Zn plus 1 is the next number of z. You have to put in numbers. You put in numbers for n or z, n and z and c and whatever. And then you run this equation 1,000 times and figure out, you have to figure out which numbers doesn't make this thing blow up to infinity.
So the way it works is you pick a number c, any number in the complex plane, and then start with z equals 0.
So now he's talking about complex plane. And I'm just going to touch onto it briefly. What that means is there's what's called real coordinates and imaginary coordinates. And the complex plane is a combination of real and imaginary. And what that means is, like, if you were to take a sine wave and go a certain distance from 0 to some portion of the sine wave, that angle that you get is along the circumference of a circle, which is the top part of that sine wave, that coordinate is related to the angle that it makes with the x-axis. And you can convert that to a real and an imaginary counterpart. I'm not going to go into that right now. I should probably talk about that, but let's just watch this.
And then iterate this equation over and over again. If it blows up to infinity, well then the number c is not part of the set. But if this number remains finite after unlimited iterations, well then it is part of the Mandelbrot set. So let's try, for example, c equals 1. So we've got 0 squared plus 1 equals 1, then 1 squared plus 1 equals 2, 2 squared plus 1 equals 5, 5 squared plus 1 equals 26. So pretty quickly you can see that with c equals 1, this equation is going to blow up. So the number 1 is not part of the Mandelbrot set. What if we try c equals negative 1? Well, then we've got 0 squared minus 1 equals negative 1, negative 1 squared minus 1 equals 0, and so we're back to 0 squared minus 1 equals negative 1. So we see that this function is going to keep oscillating back and forth between negative 1 and 0, and so it'll remain finite, and so c equals negative 1 is part of the Mandelbrot set. Now normally when you see pictures of the Mandelbrot set, it just shows you the boundary between the numbers that cause this iterated equation to remain finite and those that cause it to blow up. But it doesn't really show you how these numbers stay finite. So what we've done here is actually iterated that equation thousands of times and then plotted on the z-axis the value that that iteration actually takes. So if we look from the side, what you'll actually see is the bifurcation diagram. It is part of this Mandelbrot set. So what's really going on here? Well, what this is showing us is that all of the numbers in the main cardioid, they end up stabilizing onto a single constant value. But the numbers...
He's talking about that line in the middle, maybe?
In this main bulb, well, they end up oscillating back and forth between 2 values. And in this bulb, they end up oscillating between 4 values. They've got a period of 4, and then 8, and then 16, 32, and so on. And then you hit the chaotic part. The chaotic...
He's not really going into the other sections. If you can see the top and the bottom, these are the self-similar parts of the Mandelbrot set. They're the same. So this logistic map would occur in these other areas as well, but probably with different starting numbers, maybe.
The chaotic part of the bifurcation diagram happens out here on what's called the needle of the Mandelbrot set, where the Mandelbrot set gets really thin. And you can see this medallion here that looks like a smaller version of the entire Mandelbrot set. Well, that corresponds to the window of stability in the bifurcation plot with a period of 3. Now, the bifurcation diagram only exists on the real line because we only put real numbers into our equation. But all of these bulbs off of the main cardioid, well, they also have periodic cycles of, for example, 3 or 4 or 5. And so you see these repeated ghostly images if we look in the z-axis. Effectively, they're oscillating between these values as well.
Pretty neat,
Personally, I find this extraordinarily beautiful. But if you're more practically minded, you may be asking, but does this equation actually model populations of animals? And the answer is yes, particularly in the controlled environment scientists have set up in labs. But what I find even more amazing is how this one simple equation applies to a huge range of totally unrelated areas of science.
Okay, so now he's going into other aspects of how that logistics map formula works, and I want to jump into this one right here. This is called the Sierpinski Triangle. This stuff will come together once I get towards the end here.
Its self-similarity dimension. The fractal we'll consider now is a famous fractal known as the Sierpinski Triangle. You've likely seen it before. Here are the steps in its construction. One starts with a solid triangle, and then removes from that triangle the middle triangle, like this. One's then left with 3 triangles.
So this is something similar to, and I will look this up, it's called Life Automata, where what you do is you set up a certain number of rules. You set up certain types of rules, and things can either replicate if they're next to each other. If they're not next to each other, they destroy whatever is next to each other. Things of that nature. So you make a set of rules, and then you run the program, and you see if that's similar to the predator-prey program, where you see if the predators blow up into infinity, or if they kill all the prey, then eventually they're going to die. You know, there should be a balance, and that balance is kind of hard to find. Maybe, I don't know, but well, let's listen here for a minute.
1, 2, 3. From each of those, remove the middle triangle. Now there are 9 triangles. From each of those, remove the middle triangle, and so on.
And it looks like as you continue from left to right with these triangles, it looks like there is less dark space and more white space. So they're saying that the area goes to infinity. No, the area goes to 0, and the perimeter of all of these triangles put together approaches infinity. That's just the way this program is written. But what I want to get into is what's called the dimension. And they're saying that the dimension that if you have a number that's closer to 2, let's say, this is between 1 and 2 dimensions. So if you have a number that's closer to 2, it's more complex, and it's showing you more detail. If it's closer to 1, it's less complex and there's not as much detail. But the number that's between 1 and 2 is what's called a fractional dimension. But I could be wrong. But I'm questioning this. I'm asking a question. Is this similar to a fractional dimension, comparing, let's say, a line and a plane? You've got a line, which is like 1 dimension, and you've got a plane, which is 2 dimensions. Now, if you look at this picture, like everything written on this piece of paper is in 2 dimensions. But remember what I was talking about earlier with these chaos formulas. When you look at the pictures, it looks like there are 3 dimensions, and I didn't really get into a lot of that yet because it's a little bit more advanced. But I'm just saying from my own experience, looking at them, and even in this last one, there was a 1-dimensional formula that was an integral part of a 2-dimensional and even 3-dimensional figure. So I'm wondering if this is what's called the fractal dimension is actually related to fractional dimensions, which is the dimensions in between dimension. Who knows? You know, I'm just throwing shit out there.
As this repeats, one gets a fractal shape. So here's this carried out a few generations farther. And it's a fractal because we see these triangles within triangles within triangles repeating at many different scales. It's self-similar.
He's got a party going on
Okay.
in the background. Now this formula right here, the number of small copies equals the magnification factor to the power of d, which is the fractal dimension. This number becomes important in what's called strange attractors and some other chaos formulas. Because it's not a whole number. And how they came up with this formula to determine the fractal dimension, I'm not really sure. Maybe I could look that up or something.
Let's calculate the self-similarity dimension. So, number of small copies. I guess I'll look at this version of it, and I see 1, 2, 3 small copies. 1, 2, 3. So the number of small copies is 3. The magnification factor is 2. You can see that I need to take this and I need to stretch it by a factor of 2 this way and 2 this way to have the small copy be as big as the large one. I guess you could also see that here, that this triangle, this side is half of that, the base is half of that. So we need to magnify or stretch this triangle by 2 in order to have it be as big as the full one. So the magnification factor is 2.
And here's where we get into
the dimension is d, and we need to solve for d. So again, we'll use logarithms to do that. And let's see what we get.
Oh, what joy.
So the equation was 3 equals 2 to the d. We'll take the log of both sides. Use the exponent property of logs. And then solve for d by dividing both sides by log 2.
And this video is on Complexity Explorer on YouTube. You did a pretty good job with this.
So, there's our answer.
I got a calculator.
The dimension of the Sierpinski triangle is log 3 over log 2. And we can get an approximate decimal value for that from a calculator. So 3 log divided by 2 log equals, and I get that d is about 1.5.
So that's like halfway between 1 and 2.
5. So again, we see a non-integer dimension. The dimension of the Sierpinski triangle is between 1 and 2. So this object has a dimension of about 1.585. The next couple of quizzes will give you a chance to practice this idea of calculating the self-similarity dimension. So I'll give you a few other fractals and you'll calculate the self-similarity dimension. I should mention that in my experience teaching this, it can sometimes take a little while to see this magnification factor in small copy stuff. It's so geometric and visual that I find it's a little bit hard to explain with words, but if you do a couple of examples, eventually you'll start to see it. So try the quizzes out. If you don't get them right away, don't worry. I'll go over them in the videos after the
Complexity Explorer. He's got some pretty good videos there. Let's see here. Let's just check this one out. I haven't looked at this yet.
The side length of the triangle, in step 0, is 1 unit. Find the total perimeter of all the blue triangles in each of the steps.
So my question here would be, why do we need to know the perimeter?
The total length of the outline of a shape. Let's focus on the first 2 steps. In step 0, there is 1 blue triangle, and the sum of all the side lengths is 3. So we can write these terms as multiples of 3 by 2. as shown. Finally, for the step n, here is the perimeter of all the blue triangles. Find total perimeter of blue triangles in step 35. For this, use the formula for the nth step, as shown, and set n equals 35. And here is the answer.
Okay.
Let's look at the total area of the blue triangles at each step of the Sierpinski triangle. For an equilateral triangle, the area is given by this equation. Here, L is the side length. Let's focus on the first two steps. For step 0, considering the side length of 1 unit, the area becomes. In step 1, there are 3 blue triangles, and the side length of each is 1/2. Let's find the area of one such triangle as shown. Then multiply by 3, in order to obtain the total area of all 3 triangles. Now, to find the common ratio, divide this by the term obtained in the previous step. This gives 3/4. So our common ratio, or the multiplication factor, is 3/4. Now multiplying by this 3/4 consecutively, we can obtain the total area of all the blue triangles in step 2, step 3, and so on, as shown. So, we can write each term as a multiple of 3/4 in this form. Finally, for nth step, the total area is given by this term. Let's look at the total area and the total perimeter of all the blue triangles as n tends to infinity. For the area, write the formula for the nth step and find the limit as n approaches infinity. This can be written this way. Note, 3/4 is less than 1. As n increases, the limit of this function approaches 0. A graph of this function is shown. It can be seen, as n gets large, the function approaches 0.
It looks like a logarithmic curve almost.
Now for the perimeter.
Actually, that
Write the formula for the nth step and find the limit as n tends to infinity. This can be written in these two forms. Let's consider this first one. Since 3/2 is greater than 1, as n gets large, the value of this function increases, so the limit, in this case, is infinity. This can be seen from the graph of this function, as shown.
N looks like it's approaching a number, though. Okay, you go back to that, you see. This is
seen from the graph of this function, as shown.
This is the thing, like, in this case, this perimeter, even though the y-axis is going off to infinity, the x-axis is actually approaching a number. Unless if that's, I'm not sure exactly what that number is. But anyway, I just want to get back to the fractional dimension, and this particular equation doesn't really talk about it yet. What's this one here? Did I go over this? Oh God, what happened? Oh, we already did this.
2 to the d. We'll take the log of both.
We already did this, didn't
A
we?
chance to practice this idea of the
Yeah, I just want to go back at the beginning. So the area goes to 0. And the perimeter goes to infinity. But there's no... I mean, it's self-similar. I want to type something in here. Let's type in... Let me think a minute. Actually, what we should type in is this here. Veritasium actually talks about it, huh? Interesting. And this guy's pretty smart.
Stand down.
Oh, we have an advertisement to watch. What joy. We can skip that.
Up there with pi and e and root 2, but this one I'd never heard of until recently. And apparently, well, they're pretty sure it's irrational, so I'm just going to give you the first bit of it. This is Feigenbaum's constant, or one of Feigenbaum's constants. There's another one. If you find...
So he thought he was saying it was irrational, but if you go back, I don't know if I have that on my list, but there's what's called transcendental numbers. Numbers that have an integer, which if you think about the log of the number, there's two parts of the log. One of them's called the mantissa. I can't remember, but anyway. If you think of this number as being the log, because that's what the dimension was. The dimension was a result of the division between two logarithms.
And references to two of them. I'm not going to talk about the second one, which has a symbol alpha. There was a paper in, I think, 1970 odd by Robert May about an equation, which I'm going to write down, which models population growth. X, so it's traditional, and this is going to be like a population level. And it's a way of modeling like how things breed, so maybe rabbits or frogs. Let's go with rabbits, because they breed like, rabbits. It's going to have some other variables in it. This is what they call the logistic map. Map is like a posh word for a function. You get an input and output, and it's mapping one value to another one. But what this does is it predicts what the next year's population is going to be for a community of animals. The first component here is the next year population. So that means this one here is the previous. And so we're kind of counting populations. They're going to be between 0 and 1, like empty dead population, and a full population. And that's what this number is as well. So we've got like, we're going to iterate this. We're going to get an answer out and put it back in to get the next year's thing. And then the important number here is this lambda. It's like the fertility. So like if this is high, these things are going to breed.
That was the
like,
R number
like
in the last
and
video.
if it's 0, they're not going to breed at all. And changing this number is what the biologists were using to sort of model different populations. If the previous year's population is high, you'd expect the next one to be high. So you're kind of multiplying by the previous year's population. But also if it's too high, they're going to run out of food. So that's where you do 1 minus the previous population. So this is like the breeding.
I want
and
to
this
jump
is like
ahead
starvation.
here.
What's interesting is you can just put we had was rabbits doing this, stabilizing. And then the next behavior you had was rabbits dying. And then we've just seen something else can happen. And it happens out there in the real world, is that you start somewhere and it sort of bounces up here and then down and then but it doesn't stabilize ever, it keeps bouncing like this. And the reason this map is being used, this function is being used, is that it's capturing even more complicated behaviors than just life and death. So we've got life, but high population, too many rabbits, so they kind of die off, but next year there's loads of space for them, so they grow again and then they bounce. I'm going to pick lambda to be, this is a carefully chosen value, I'm going to pick it to be 3.5. Let's try that one. I'm going to set the population to be a half. 3.5 is lambda multiplied by the previous population multiplied by 1 minus the previous population. This time it goes up to 0.875, 0.38, 0.82, 0.50. Wait, these are all different. I'm just going to keep pressing it. But it's definitely not settling down. I'll show you what's happening on the screen. We've got 0.5, 0.87, 0.38, 0.82, 0.5, 0.87, 0.38, 0.82. Actually, it is cycling, but it's not 2. It's now 4. And so if I drew a graph of this one, this time it's going sort of down, up, down a bit further, up a bit further, and then down, up, down a bit further, up a bit further. So actually we've got a 4 cycle. At this point, like doing this on a calculator becomes a bit of a waste of time. But what the biologists were doing with a computer was saying, okay, even complicated behavior like a 4-year cycle of populations can be modeled by this with still just this one parameter, this one fertility thing. And that surprised them. What they didn't know was about to happen was what happens if you go above 3.5, because no one ever did, because it looked like it didn't do anything useful. If you change lambda beyond roughly 3.59, something strange happens, which we should try and see on a picture. I'll do a little graph here. This is going to be, this time it's not time. This is going to be the lambda axis. So I'm going to capture different values of lambda, the fertility on this axis, but this is still going to be population between 0 and 1. I'm going to mark this at 4, and this is 1. So this is the behavior after it's settled down. So between 0 and 1, it turns out that if you pick lambda between 0 and 1, eventually things die. As you nicely exemplified, you killed all the rabbits because they're not fertile enough. So after you've pressed equals thousands of times, we're going to plot what happens.
So this is the death zone.
This is the death zone, yeah. Well, maybe we should write death here, because over time, the population stabilizes at 0. You chose 0.6 something, and it was in the death zone, so this was kind of your point here. When we did it earlier, we chose 2.3 here, which is about here, but it stabilized to be about 0.56. I think it was 0.565 when we did it, so it's kind of just over half. So there's a mark on our graph here. And if you do this, and you could plot this on a spreadsheet if you wanted to, you see that the stability changes in this sort of pattern, in that different values of fertility give you different stable populations. Interestingly, it sort of levels off at about 2/3. It looks like you can't have a stable population that's fuller than that, according to this model. But you've already seen that something interesting happens. We tried 3.2, I think, earlier. So 3.2 gave us a 2 cycle, which means over a long time, we're going to have 2 marks on this graph. And so I'm just going to sort of estimate that they were about here and here. And the graph, if you plot it, bifurcates, which is a posh way of saying it forks. Like they call it a pitchfork bifurcation. And so this is, we've got dead, we've got stable, and then from about 3, we get a 2 cycle. But we have also seen that at 3.5, it settled into a 4 cycle. So then you can kind of guess what's going to happen. If I put the 4 on, they happen to be around here, and you can see that somewhere it splits. And it bifurcates again, or it forks again. The posh word for this is the period of these cycles. This is a 1 cycle because it's got 1 value. This is a 2 cycle, the period is 2. And then it goes to 4. And they call this a period doubling thing. What's intriguing is that by picking certain values of lambda, you can get any period you want, as long as it's a power of 2, because it doubles every time. So if you want a 16 cycle, there is a value of lambda. I'll let you go and find it. It's not much higher than what we used at 3.5, because come and have a look at this graph again. The graph doubles again, and again, and again, and again, and quicker, and quicker, and quicker. So a tiny change in this lambda gives you a new branch. And it gets insane. It gets so that you can't make any change even to the accuracy of your calculator and expect to notice the difference, but massively different behavior is happening. And if you recognize this sort of thing, this was being studied before the word chaos was used. But we now understand technically the word chaos, apart from just being a mess. It means technically something which is really sensitive to initial conditions. So this is a good example. A tiny change in our lambda gives you massively different behavior. And from a modeling point of view for rabbits, this stops getting useful because it becomes very hard to predict what's going to happen with a certain value of lambda. But there is a final twist. Before we get to a final twist, which is what happens to that graph further to the right, Mitchell Feigenbaum got involved in this at this point in the 70s. And he was looking at this thinking, it's surprising that a simple function does an interesting thing like this. And he started to study how quickly this doubling happened. So that took a little gap. And this took a shorter gap. And this takes a shorter gap again, because it's going quicker and quicker. And he thought it'd be interesting to know if this is a sort of regular scaling thing. He didn't think it would be, because it's doing crazy stuff. But he started dividing one of these regions. So like if you divide that width by that width, and then that one by the previous one, just to see the ratio. And he got this number, Feigenbaum's constant it's called now, 4.669. Now, in itself, it's quite amazing this has a nice regular behavior. What it's saying is that this gap is about 4.6 times smaller than the previous gap. So the period doubling is getting quicker and quicker. It's a geometric series, in fact. If you multiply that by 1 over 4.669, you roughly get this one. And if you keep going, he managed to prove that this is the ratio it's tending towards. But he doesn't know what this number is, and still no one knows actually what this number is. We don't have a closed form of explaining what this number is. What is genuinely shocking is that he then looked at some other equations. Forget biology now. He just looked at other quadratic equations. If you haven't spotted already, I'm just going to point it out. this equation here is a quadratic because it has an x times an x. He looked at all sorts of other functions, all of them having a single sort of hump, and this is a quadratic map with a single hump. And he found that every function he looked at not only exhibited this period doubling, if you started fiddling with a parameter, but it also scaled with that number. And it turns out now this is called Feigenbaum's constant because every unimodal map or quadratic map scales like this. And no one knows what this number is or why things are behaving like this, but it seems to describe a whole raft of things which no one had ever looked at before. And there was this concept of universality, that even different situations are still captured by this number. So I'm going to recreate the diagram we had earlier on paper. I'm just going to start that here. So we've got our lambda along here, and this little red dot, which is now tracking across. We're in the dead zone here. This is where population is dead, but after 1, you can see it spikes up. So this is a stable population now. And it's going to go all the way to 3 before it does. You remember what happens. It's going to split, bifurcate at 3. So that's our 2 cycle. And then I told you that it does something around about 3.4, just a little bit afterwards. I'll show you that now. Splits again. So that's our second bifurcation. But you know it's going to get quicker and quicker. This is what Feigenbaum found. So after this, it's going to period double very, very, very quickly. But actually at a point which is about 3.59, it's not very far away, you can prove the period doubling must stop at that point, because that would be like if you add a geometric series up to infinity, there's a limit. And so the prediction doesn't tell you what happens after that point. But you can see it. We can go beyond infinity right now. So at 3.6, the period doubling is going to stop and something else is going to take over.
So when he says beyond infinity, I'm going to just look at my... my title has multiple infinities in there. You know, how can you go beyond infinity? The only way you can do that is if you have an equation that's in one dimension, but you're actually looking at it, you're actually seeing another dimension. There's another dimension there. So it's like curving, like in the previous video that Veritasum had, where he turned the axis and made it like this is actually looking at a two-dimensional part of the Mandelbrot set. So if even still, if you're thinking in terms of twisting this back so that it's just a line, you know, it's still going off into infinity over to the right. So I'm not sure exactly what he means there.
Watch this. So there's a very strange behavior. It's nice and simple and then crazy. And actually this is a good example of chaos as well. I'm going to zoom in on that region. So here's the 2 cycle, and then it's split again to a 4 cycle, and then 8, and then 16, and then right there we've gone in what they call the onset of chaos. And it's a technical term, chaos meaning really sensitive, but it's almost beautiful. There's weird structure happening here. This is not a glitch in my software. And yet it looks like for most of it, it's spitting out random. So these are the populations. Every time you press equals, it's creating a dot.
So now we're going back to the other video where this is part of the Mandelbrot set, and we're looking at it from the side. It's interesting that you've got, would be like noise. This would be like all random stuff. But you can see lines in here. And these lines are like there's this central point here where all these lines are coming out of. It's just interesting that there's other stuff going on in here. Yeah, that Feigenbaum constant's kind of interesting though.
Does this get crazier then, like the Mandelbrot set?
You're right to spot that. The Mandelbrot set is involved with this. This is a fractal. If you zoom in on stuff, so if I zoomed in on this period doubling bit, you can see more period doubling is self-similar. But then the self-similarity seems to sort of go a bit crazy. Actually, this is the Mandelbrot set, but you're only seeing one dimension of it. The Mandelbrot set, as you may know, is all about using complex numbers. You need two-dimensional numbers. If you just looked at the central line of the Mandelbrot set and plotted what the points do when you do the iteration, this is what you're seeing.
So these are the real number counterparts without it's on the some aspect of that line is 0 in 3 dimensions. Whether it's X, Y, or Z, I don't know which one. Let me go back here. Let's do this. We're going to do this one right here, this video.
In this last segment about maps, I'm going to talk about...
Okay, so I watched this lady here. I watched this video already, and this is not what I'm going to look at. She was very confusing. Let's watch this.
Sponsored by LastPass.
Again,
More
we
about
have Vera.
the end of the show.
The butterfly effect is the idea that tiny causes, like a flap of a butterfly's wings in Brazil, can have huge effects, like setting off a tornado in Texas. Now that idea comes straight from the title of a scientific paper published nearly 50 years ago. And perhaps more than any other recent scientific concept, it has captured the public imagination. I mean, on IMDb, there is not one, but 61 different movies, TV episodes, and short films with butterfly effect in the title. Not to mention prominent references in movies like Jurassic Park, or in songs, books, and memes.
I'm going to jump ahead
Oh,
here.
the memes. In pop culture, the butterfly is the hallmark of chaos. Now, since Lorenz was working with represented a toy, maybe a vacuum tube had blown, but none had. The real reason for the difference came down to the fact that
Grammarly does more than catch errors.
Yeah, I know that, but
With
not on my
Grammarly, you can
show,
find
it
really good.
doesn't.
No.
All right, let's skip ads. And
rounded to 3 decimal places, whereas the computer calculated with 6. So when he entered those initial conditions, the difference of less than 1 part in 1,000 created totally different weather just a short time into the future. Now Lorenz tried simplifying his equations and then simplifying them some more, down to just 3 equations and 3 variables, which...
So here we have the introduction to differential equations, or not. This actually isn't a differential equation, but it looks like it's how x varies over time, how x, y, and... Wait a minute. It's showing how x varies over time, which is, I think that's symbol is called rho times y minus x. And the next one is x times p minus z minus y. This is a 2-dimensional equation. But now he's got dx over t, again, equals xy minus bz. So that's actually a transformation of a z coordinate back to the x-axis, I think. And maybe that explains why it looks like it's a 3-dimensional object.
Represented a toy model of convection, essentially a 2D slice of the atmosphere, heated at the bottom and cooled at the top. But again, he got the same type of behavior. If he changed the numbers just a tiny bit, the results diverged dramatically. Lorenz's system displayed what's become known as sensitive dependence on initial conditions, which is the hallmark of chaos. Now, since Lorenz was working with 3 variables, we can plot the phase space of his system in 3 dimensions. We can pick any point as our initial state and watch how it evolves. Does our point move toward a fixed attractor or a repeating loop? It doesn't seem to. In truth, our system will never revisit the same exact state again. Here, I actually started with 3 closely spaced initial states, and they've been evolving together so far, but now they're starting to diverge. From being arbitrarily close together, they end up on totally different trajectories. This is sensitive dependence on initial conditions in action. Now, I should point out that there is nothing random at all about this system of equations. It's completely deterministic, just like the pendulum. So if you could input exactly the same initial conditions, you would get exactly the same result. The problem is, unlike the pendulum, this system is chaotic. So any difference in initial conditions, no matter how tiny, will be amplified to a totally different final state. It seems like a paradox, but this system is both deterministic and unpredictable. Because in practice, you could never know the initial conditions with perfect accuracy, and I'm talking infinite decimal places. But the result suggests why even today with huge supercomputers, it's so hard to forecast the weather more than a week in advance. In fact, studies have shown that by the 8th day of a long-range forecast, the prediction is less accurate than if you just took the historical average conditions for that day. And knowing about chaos, meteorologists no longer make just a single forecast. Instead, they make ensemble forecasts, varying initial conditions and model parameters to create a set of predictions. Now, far from being the exception to the rule, chaotic systems have been turning up everywhere. The double pendulum, just two simple pendulums connected together, is chaotic. Here, two double pendulums have been released simultaneously with almost the same initial conditions. But no matter how hard you try, you could never release a double pendulum and make it behave the same way twice. Its motion will forever be unpredictable. You might think that chaos always requires a lot of energy, or irregular motions, but this system of 5 fidget spinners with repelling magnets in each of their arms is chaotic too. At first glance, the system seems to repeat regularly, but if you watch more closely, you'll notice some strange motions. A spinner suddenly flips the other way. Even our solar system is not predictable. A study simulating our solar system for 100 million years into the future found its behavior as a whole to be chaotic, messy. But soon all the points have moved towards or onto an object. The object...
And of course we have another advertisement to go through here. Oops, what's going on here?
Incidentally, looks a bit like a butterfly. It is the attractor. For a large range of initial conditions, the system evolves into a state on this attractor. Now remember, all the paths traced out here never cross, and they never connect to form a loop. If they did, then they would continue on that loop forever, and the behavior would be periodic and predictable. So each path here is actually an infinite curve in a finite space.
My bird. Shut up, bird.
But how is that possible? Fractals, but that's a story for another video. This particular attractor is called the Lorenz Attractor, probably the most famous example of a chaotic attractor, though many others have been found for other systems of equations. Now, if people have heard anything about the butterfly effect, it's usually about how tiny causes make the future unpredictable. But the science behind the butterfly effect also reveals a deep and beautiful structure underlying the dynamics, one that can provide useful insights into the behavior of a system. So,
and you know, there's also artistic possibilities messing around with these chaos formulas. There's art, there's a lot of stuff going on there. But anyway, let's look this up here. I want to see if I can find something here. Cellular Automata. Yeah, let's see what this is here.
Hi, today we're going to talk about Cellular Automata. The singular of Cellular Automata, by the way, is a cellular automaton. So we're going to look at a cellular automaton, but we're going to discuss cellular automata. Now, why? First of all, what is a cellular automaton, and why are we looking at this? Okay, so first of all, you know, you might be just arriving here from nowhere, which is totally fine, but if you had just watched the previous video, the last thing we talked about is right here behind me, a flocking system, a complex system, a system of many simple agents that when they work together exhibit this,
what he's talking about?
Exhibit this complex intelligent behavior. So there's a lot going on in this system. There's physics, there's motion, there's all sorts of stuff. The neighborhoods are changing as these things move about the space. one of the reasons to look at cellular automata is to say, okay, now that we achieved this complex system, let's boil that down and try to create
this is
the
called the
simplest
coding
possible
train
complex system ever.
on YouTube.
What would that be? What is
I've
the
never seen this
simplest
video, so I don't know
possible
what it's gonna
agent
get into
which would
here.
have the simplest possible neighbors and the simplest possible set of rules as to how it interacts with its neighbors? If we could design that system, could we still achieve complexity? So that's the question we want to answer when looking at cellular automata. Now, what is one? Well, okay, first of all, so these videos we're basically going to talk through the two classic examples, and we're going to do them in reverse chronological order, but our order is going to have some logic to it. So I'm just going to move. So we're going to go through two kind of classic cellular automata. This one is scrolling here by, this is the Wolfram Elementary CA, and this is rule 30? 30? It is, in fact, this is rule 30, which we're going to get to. What does rule 30 even mean? This is, we're going to talk about Wolfram in a little bit. Over here we have something called the game of life, which is perhaps the most famous, or certainly the first most famous cellular automata that sort of...
If you look at that game of life, it looks like it settled down. It settled down to a state. Like before, it had some stuff moving around, and now it's like there's nothing changing. So it's settled to a constant value.
Arrived into popular culture with a well-known article in 1970 in Scientific American. So,
and another reason why this is a bit of a problem, and I don't think the coding is correct, because I think what you need to do, like this is bounded on the x and y axis. So I think what needs to happen is that the x and y axis, they need to overlap so that the end of the x axis goes back to the beginning, like it's a whole plane. And I think in this situation, the way they've got it set up here, I don't think it's like that. I think it's just x goes to 100 and y goes to 200 or something. And it doesn't overlap. Like x at 101 should overlap back to x equals 1 here. And it doesn't look like that's happening, because if it was, you would see parts of the diagrams on the left, you'd see them on the right here. And I don't see that happening.
So we're going to look at these two systems, understand how they work, understand how to write the code
one on the
for
right
them, and
is
then
the one
ask
I'm
the
interested
question.
in.
You know, great, we could just implement these and change the colors and we have some interesting patterns, but really we need to ask the question, how does this way of thinking apply to the type of work we're doing in interactive media, computer graphics, computational design, all that sort of stuff.
Art,
so hopefully
music.
this video is going to kind of introduce the concepts behind these two systems, and the next couple videos will walk through the code for them, and the last video will kind of talk about other possibilities in this realm. Okay, do we feel good about that? I feel good about that. Yes. So let's define, let's just say CA. Let's define a CA. Okay, let's define a cellular automaton. A cellular automaton is a grid of cells. We're going to look at one-dimensional grids, two-dimensional grids. A one-dimensional grid, for example, just looks like this. Here are a whole bunch of cells sitting next to each other in one dimension, which incidentally looks quite a bit like the diagram for an array. So we can see how this is going to fit nicely in terms of programming these types of things. Okay, now, if a CA is a grid of cells, each cell is defined as an entity that has a state, and we're going to look at a variety of possible states, the simplest being a 0 or a 1, right? A binary state. It's on or off, alive or dead, 0 or 1, black or white. And each cell also has a neighborhood. This is very important because how a cell's state changes over time is going to be determined by the sum, by analyzing its neighbor's state. So this is really the third aspect of defining a CA, which is that the state of a cell,
so
a
this
cell
is really
state
setting up
at any moment in time, t
you could set
is
like
equal
a predator
to a
prey, or
function
you could
of
set up
the
your
neighborhood
birth and death rate of a system.
states at time t minus 1. So we have this idea of generations.
This gets a
Generations
little
over
bit away
time.
from
the
my
CA has a
original
whole bunch of
topic of
states if
dimensions.
there's 0 or 1s. And then we say, hey, at the next moment in time, this state cell is somehow going to be calculated
But
based on
dimensions
a
could
neighborhood
still
of
be
states.
here.
Adding them together,
And what if a
averaging them, say,
dimension
what
is
the
a number
pattern,
that
type
could
of thing.
determine
So this is how we define
an initial
a CA.
condition or
Great.
initial states of existence too?
So I think this actually, strangely, I'm trying different things, wraps up this video. And I guess I'll give you an exercise, which is kind of a bit of an insane one. But you know, many of you watching this might be familiar with this already. Many of you watching this might have never heard of a CA before. If you haven't, try to design for yourself a set of rules for how cell states would change over time for a one-dimensional CA with zeros and ones. Now this is, of course, what we're going to look at in the next video. The next video we're going to look at the Wolfram elementary CA, which is precisely this. A one-dimensional CA where the states are zeros and ones, and we're going to look at...
Yeah, let's just go ahead and do that and see what he's got here.
All right, we're ready to look at our first cellular automaton. Now, road. But let's go through each of these and say, what is the simplest possible scenario? Well, a grid of cells, the simplest possible grid of cells would be a one-dimensional grid, a linear grid, so to speak, an array of cells. The simplest possible set of states would be a 0 or a 1. I suppose the simplest possible set of states would be just 0, but we couldn't possibly get anything out of just having one state. So we at least need two states, 0 or 1. Now, we have a slightly more interesting question here, which is, what is the simplest possible neighborhood? Well, let's say we're talking about this particular cell. We might state that, you know, the simplest possible neighborhood, it could be just to the left or just to the right, but I'm going to say the simplest possible neighborhood is the 3 adjacent cells, this cell and its neighbor to the left and to the right. So if this is the simplest possible neighborhood,
so that's
one cell with its left and right neighbors. Am I recording? Yes. Now we have to ask our question,
0, 1, 1, 0, and 1,
how
1.
do we write the rules for the elementary CA where we get the cell state
so you
is
could
a function?
You could say if 1, 1 exists, then the state is going to be 0. If 0 or 1 exists, then the state's going to be 1. You could make this an AND gate. You could make it an OR gate. That's some digital notation, depending on what he's doing there. You could do it that way.
Of its neighboring
See if
states
I'm close.
in the previous generation. Okay? So this is our project right now. We need to walk through these rules, define them, and then see how they're implemented in code.
If it's 0,
and then
1, it's
we'll
1. If
look
it's
at the
1
results.
and 1, it's 1.
Have the results achieved anything interesting, or a value, or have they achieved complexity? So let's answer that question.
If
So
it's
I'm gonna
0 or
erase this.
1,
We
let's
can
make
kind of
babies.
remember this. And let's look at a little bit more detail here. So let's say this is our CA.
Now, I'm still
This is our
thinking in
CA
terms
at
of,
generation.
are there
Big
a
anal
constant number that
This
shows
is
up?
generation
Is there
0.
a dimension that
Generation
shows
0.
up?
This is our CA. Okay, and we're going to give it a bunch of cells, states.
Depending on the formula.
And what I did here is somewhat arbitrarily, I made a bunch of zeros and I gave one cell a state of 1. The reason I did that is this is kind of the classic or standard way of demonstrating a CA, is to say, let's have all the cells be off and just put the center one to 1. I don't know if that's actually the center one, but close enough. So we have to ask ourselves, how do we evolve?
Actually, if that 1 would never exist because he's got previous zeros here. So, I mean, I don't know.
Generation 1. I probably shouldn't have used the word evolve. I don't think technically there's any evolutionary computing going on
I
here,
see what he's
although
doing.
that is something
Okay.
we're going to examine in a
Okay,
future
so
video.
he's going
How do
down
we
would
compute
be
the next generation would be more accurate.
would be time.
Okay, so this is our neighborhood. Now let's think about this. What
The
is
whole
this
line
here?
is
This
the neighborhood.
that's going to give us, at the very least, the state for that particular cell at generation 1. How many possible ways could that neighborhood be configured? Well, that neighborhood
4.
could be 0, 0, 0, or 0, 0, 1, or 0, 1, 0, or 0, 1, 1,
Oh,
or
now
1,
he's
0,
doing-
0, or 1, 0, 1, or 1,
he's
1,
doing
0, or 1, 1, 1, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so, we should admit something to ourselves.
No, that's...
There's a lot of binary number stuff going on.
That's really
here.
not quite correct because there's only 4 states. Because the number in the middle is 1. Okay, so there's 1, wait a minute, 2, 3, and 4. There's only 4 states. I don't know why he would add the other 4, because 0, 1, 0 is going to be either 0, 1, 0, 0, 1, 1, 1, 1, 0, or 1, 1, 1. It can't be these other ones. Unless if he's using a different rule that I'm thinking.
I enjoy that. I think it's sort of fun. You got zeros and ones, and it makes you look like you're kind of a mad, crazy person with writing all these zeros and ones. But really, you might remember this whenever you started first working with computers or learning to program, or if you've had to work with a microcontroller. What we have here are 3 possible ways of having a number with a 0 or 1 in it, or we have 2 to the 3rd power possible way configurations, or 8 possible configurations. 1, 2, 3, 4, 5, 6, 7, 8. So what's interesting to note is there are only 8 possible ways that neighborhood could be configured. So if there's only 8 possible ways, why don't we just define an outcome for every possible way? Meaning, if the neighborhood is configured like so, the resulting new state should be a 0. If it's configured like so, it should be a 0. If it's configured like so, it should be a 1. Then let's say a 0. Then a 1.
Now he's just arbitrarily picking up numbers here.
And then a 0. Right? So I made up an arbitrary rule here. But in a Wolfram elementary CA, this is what is known as a rule set.
Right.
Now, somewhere in my magical annotation system to this video, you will see the decimal equivalent of this, right? It's some number. I can't do this binary stuff in my head. I wish I could. That would be cool. I could secretly pause and re-record the video and make it look like I know this. But
well, if the base is it's 1, 2, 4, 8, 16, 32, 64, 128. So you just pick one of those numbers and you've got a number there. It's base 8 or whatever. But I mean, I would have chosen, he's got 4 1s there. He didn't really talk. He should have been a little bit more explicit in his rule. It would make a lot more sense. You could say if either, like I said before, if either or one of the neighbors is a 1, then the middle one is going to be a 1. He's trying to determine the state of what that 1 is. But like you said, you've got all these other variables happening. I was just going by my rule. But then what if then you've got 2 more 1s that you're creating? So as each generation goes down, it's adding and subtracting stuff. This would be like your beginning situation, and you would have to do this 1,000 times to see whether or not it goes off into infinity, or if things goes into randomness. I wonder how you could determine what is the equation for this situation. Is it, if you've got a certain number of cells and a certain number of, this is like combinations and permutations and shit.
So if you look at this, this is the rule set. This is called the rule set. And now we have to ask ourselves another interesting question. So we looked at this and said, okay, there are 8 possible ways a neighborhood could be configured. Now, how many possible rule sets are there? Well, a rule set requires 8 binary numbers. 2 to the 8th power is 256. That I do happen to know by heart or have memorized or somehow calculated in my head. I'm not sure which one.
256
so
different
interestingly
rule
enough,
sets.
there are only 256 possible ways a Wolfram elementary CA can be defined. Which means we can look at very easily. If you got 15 minutes, we can look at, if you're not too busy, we can look at all the possible configurations. We can see all the possible outcomes. And we're going to do this in a moment. What's really interesting about this is that Wolfram actually categorizes all the possible outcomes into 4 classifications. One is called uniformity. Another is oscillation. I would say oscillation. I don't remember if that's actually what it's called. I like to think of it alternating values. Oscillation.
This is similar to what we've been talking about here.
I like to pause this video and fix what I'm thinking, but I'm just going to keep going. Another is random. And then we have complexity.
Oh, well,
so
he's calling
you
it
might imagine getting the first 2 components, the first 2 classifications, right? If we look at this and we look at, okay, well, 0, 1, 0 in this system, 0, 1, 0 means you get a 1. And let's look at like 0, 0, 1 here would give us this value. 0, 0, 1 gives us a 0. And then 1, 0, 0 gives us a 1. Hey, look at that. We got 0, 1, 1. So we look at this, we could imagine like we're just kind of, sometimes we're flipping numbers, sometimes we're not. We might get
that's another problem, because if he's going to do that, then he should have started from the beginning of the sequence, not from the middle. He should have started from the first 3. I don't know. It doesn't. It's
everything just becomes 1s, or everything just becomes 0s, or everything goes 0, 0, 1, 0, 0, 1. Repetition, that would be perhaps a better name. Instead of, I don't know why I was thinking of oscillation. You could think of it as an oscillation between states, but repetition, right? You could have uniformity. Everything tends towards just one state. Everything goes to 0, everything goes to 1, or some type of repetition.
Like
0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. We could make up all these songs, like Cellular CA songs. 1, 0, 1, 0, 1, 0.
Get to the point.
Okay. So that's what you would expect. But what's really shocking or kind of exciting or interesting about this stuff is the fact that we get, not only do we get these sort of obvious results, we get completely random results, essentially. We essentially get a pseudo-random number generator out of just a CA.
Okay, let's just jump ahead here.
A page in Wolfram's Math World about elementary cellular automata. It's an automaton, and more. We're talking about many of them. They're automata. But look, we can see here is a given rule set. If we have 3 black cells or 3 cells with a value of 1, then we get a 0. If we have 1, 1, 0, we get a 0. You can see how this is modeled. Now, if we go down, we can see here, this, by the way, is the outcome of every single possible rule. So if we look at, hey, Rule 88, and again, Rule 88 is just simply the decimal representation of the binary number 88, which would be 0, 0, 1, 0, 1.
That's okay. Okay, so this is interesting. Now, this is getting into more in-depth. As you can see, this Sipinski Triangle over here. This is how the Sipinski Triangle is generated using this Cellular Automata. I call it Automata. So there's a bunch of other different things going on. Like in Rule 86, it doesn't quite look like Rule 82. Interesting.
Blah, 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 blah. So, but what are these patterns that are being drawn? How does this relate to a one-dimensional CA? So the thing that I should mention that I think is really important is when you look at sort of visual representations of this stuff.
So there's dimension here.
You will see a two-dimensional image. Why is it a two-dimensional image? It's because the way we're visualizing it is we're stacking all the generations. So it's really important to note that the system is a one-dimensional system. This grid is one-dimensional. There's a one-dimensional array of cells, each with a state. But when we want to visualize the result and see what pattern we get, what pattern emerges, what we're doing is we're looking at all the generations stacked. And the reason why I'm I'm just like saying this over and over again is because we really are going to look at something in a moment or in a future video, which is a two-dimensional CA. The two-dimensional CA is really a grid of cells. And each state we're going to look at as a different frame of animation. But this is one generation, right? In the 2D CA, this is a single generation right here. Yes, I'm on camera. And this is a one-dimensional CA where each generation is a given row in this pattern.
So those dimensions are all between 1 and 2
now, if we go back to processing here, we're going to see, first of all, I'm representing...
Time is involved in this.
Here, I'm representing the rules as an array. So you can see this is rule 222. This is the binary representation of the number. In the comments, we're showing the decimal, 190, 30, 110, and 90. These are some rules I want to take a look at for the different Wolfram classifications. So let's run this first one, and we can see, yes, this is what you would expect. And in addition to stacking the generations that I've talked about over here, what I'm doing in this particular scenario is letting them scroll by. So we can see this is uniformity. All the cells just tend to the same state. Now let's look at repetition, which rule 190 is an example of.
Can I do the same thing in my programs?
We can see this. Now it looks like, I don't know if you, maybe if I zoom in here a little bit, you can see there are these kind of diagonal lines, it looks like. But you can, we have some kind of, this is making me crazy. We can see that it's black, black, white, black, black, white, black, black, white. That's the pattern if you look at any given cell from generation to generation. So how is this stuff being calculated? So I want to look a little bit, I'm going to switch here to the kind of simpler example, which is just showing, this is rule 90, I believe, which is, by the way, kind of amazing that with this simple system, what is this pattern? This is the Sierpinski Triangle. It's a fractal pattern, which we're going to get into more in future videos, or previous videos if you're watching these out of order. Okay, so what's going on here? I just want to point out a few things. One is that the cells are represented as an array of integers. So a given generation is an array of integers. 0, 1, 0, 1, 1, 0, 1, whatever it is. That is the array, that is that generation. This is not my best video, but I'm going to keep going. Okay, this function here, generate, is the key function for how we get the next generation, right? If we have an array of cells, right, we have an array of cells.
Well, he's getting into programming.
This here. What do we need to do to get the next?
And I want to avoid that because that's a whole different subject matter. But so he's scrolling up there. I guess he was scrolling up. I wanted to talk about these dimensions. Let's see. I was looking at logarithms. Wait, that's not set up right. Let me just hook this up here. Should be window capture. Logarithms. That's how we found this dimension. So if you have a number like 10 squared, the number 2, the log of 100 is 2. Logarithm base 10, b equals 10 is also called a common logarithm. So here you got motivation. You got 2 cubed equals 2 times 2 times 2 equals 8. The general case is when you raise a number b to the power of y, you get x. B to the y equals x. Y equals the log of b times x. Didn't really want to get into all of this. I just want to talk about this number that they had in the Sipinski Triangle. They had the number of repetitions equals the number of the scaling to the power of d. So it ended up being a log number divided by another log number to give you the dimension. It's my bird. But in a lot of these fractal fractal pictures, how are you going to be able to determine this information using logarithms? I don't think you can. Oh wait, it talks about it down here. There's a little bit of derivative stuff in there. Shut up. Tell my bird to shut up. There is arithmetic geometric mean approximation to a number. I'll have to get into that. Logarithms are linked to self-similarity. For example, logarithms appear in the analysis of algorithms that solve a problem by dividing it into similar, smaller problems and patching their solutions. The dimensions of self-similar geometric shapes, that is, shapes whose parts resemble the overall picture, are also based on logarithms, as we saw earlier. I'm just going to read this. The sum is over all possible states of the system in question, such as positions of gas particles in a container, etc., etc., etc. Entropy in information therapy measures the quantity of information. If a message recipient may expect any one of n possible messages with equal likelihood, then the amount of information conveyed by any one such message is quantified as the log base 2 of n bits. That has to do with some digital. Okay, wait a minute. Lyapon of exponent is this number here. Use logarithms to gauge the degree of chaoticity of a dynamical system. For example, a particle moving on an oval billiard table. Even small changes of the initial conditions result in very different paths. So, what is Lyapon of exponent? That's my bird. This is where it gets crazy. Whereas the global Lyapunov exponent gives a measure for the total predictability of a system, it is sometimes of interest to estimate the local predictability around a point in phase space. This may be done through the eigenvalues of the Jacobian matrix. The eigenvalues are also called the local Lyapunov exponents. A word of caution, unlike the global exponents, these local exponents are not invariant under a nonlinear change of coordinates. Put that in your pipe and smoke it. My bird. There are many different ways of constructing a Sipinski triangle. I happen to like the way that he constructed it using that rule set. Does that work if you completely bound the outside of the perimeter rather than scrolling it up like he was doing? The chaos game. This method is also called the chaos game. It is an example of an iterated function system. See, eventually I'd like to be able to program this stuff. That's this Conway's Game of Life, huh? That's one with all the triangles. I mean, with all the rules. Apophysist software and rendered by the Electric Sheep. Seems like I had this a long time ago. I don't know what this is, so I'll check it out. An iterated function is a system of finite of contraction mappings in a complete metric space. As you can see in the right-hand corner here. System of functions has a unique, non-empty, compact, closed, and bounded fixed set S. Early examples of fractals which may be generated by an IFS include the Cantor set. I'm thinking IFS is a non-bounded and iterated function system. First described in 1884. A golden square fractal. Huh. This is the number phi. And they're made a fractal out of this? How do they do that? I don't know. That's just a number that goes to some infinite number towards phi by doing this equation. I don't see how that's a fractal, though. Golden squares with T branching. Golden square fractal. Decimal expansion. The golden ratio's decimal expansion can be calculated directly from this expression. However, the square root of 5 can be calculated with this method, starting with an initial estimate such as x, whatever that is, equals 2 and iterating. Xn plus 5 over xn divided by 2 equals the next number. Newton's method can be applied directly to an algebraic equation, including the equation x squared minus x8 minus 1 equals 0 that defines the Gaussian golden ratio. Yeah, I know about that. However, this gives an iteration that converges to the golden ratio itself. X squared n plus 1 over 2xn minus 1. The time needed to compute n digits of the golden ratio is proportional to the time needed to divide two n-digit numbers. This is considerably faster than known algorithms for the transcendental numbers. Easily programmed alternative using only integer arithmetic is to calculate two large consecutive Fibonacci numbers and divide them. Shut up. Golden ratio has to do with the Great Pyramid. All that good stuff, which is interesting. What do we got here? Open source fractal flame editor. Okay. I may have to check that out later. Electric sheep. A screensaver. Check it out later. My bird's funny. A little bit more math than I want to get into, that I need to get into actually. I'll see that picture looks three-dimensional. A different 2D analog of the Cantor set is the Sipinski carpet. Yeah. We did the triangle. This is the Chaos game, huh? I don't think I've ever seen this before. For example, a point inside a square repeatedly jumps half the distance towards a randomly chosen vertex. But the current chosen vertex cannot neighbor the previously chosen vertex if the two previously chosen vertices are the same. This is easy stuff to program. It's just a bunch of loops and stuff. Or actually, if statements. I might save this one. Conway's Game of Life. It looks like this plane is like sending bombs down to the ground or something. Gosper's glider gun, creating gliders. That's cute. So these are rules. Any live cell with fewer than no two live neighbors dies, as if by underpopulation. The universe of the Game of Life is an infinite two-dimensional orthogonal grid of square cells. Every cell interacts with its 8 neighbors. They even have names for these. Heavyweight spaceship. It's like you could have these spaceships running around attacking things. Let's see if they survive, huh? This looks pretty cool. I don't know if I could program this or not. Conway's Game of Life. Cellular Automaton. Etc., etc., etc. Die Hard. Conward offered a prize of $50 to the first person who could prove or disprove the conjecture. Conway originally conjectured that no pattern can grow indefinitely. That for any initial configuration with a finite number of living cells, the population cannot grow beyond some finite upper limit. This is a whole project in itself. A nested loop. A nested for loop considers each element of the current array in turn, counting the live neighbors of each cell to decide whether the corresponding element of the successor array should be 0 or 1. The successor array is displayed. For the next iteration, the array swaps roles, so that the successor array in the last iteration becomes the current array for the next one. The game of life on the surface of a trefoil knot. Why would they even do that? Because they can, I guess. Listen to that stupid bird, huh? Okay, look at this one on the right here. Red glider on the square lattice with periodic boundary conditions. Huh. Looks like it's following the same pattern. And it looks like it overlaps, too. Listen to that stupid bird. I get on here and talk about stuff, my bird's gotta go ape. A sample of a 48-step oscillator along with a 2-step oscillator and a 4-step oscillator from a 2-dimensional hexagonal game of life. Rule H:B2 divided by S34. Let me look this up. There's some good stuff here. Wait, what's this? What's this here? Notable programs. First written in an early version of Algol 68C. Oh my god. There are now thousands of Game of Life programs online, so a full list will not be provided. Golly is cross-platform open source simulation system for the Game of Life. You have to have Lua or Python scriptability for both editing and simulation. See what this is here. Google time, Google time. SourceForge.net. I wonder if they have, let's see, let's try something here. Play John Conway's Game of Life in your browser. Hang on just a second here. What we got going here? This should show up here. My bird's like, uh-huh. Alright, let's see what happens. Well, that didn't work out very well. They just disappeared. Let's see. How'd they just disappear? YouTube. Yeah. I think this would take way too long. I think you'd have to, oh, whoa. Holy shit, this is huge. You'd have to put a whole bunch of stuff on here. Actually, wait a minute, let me refresh this. Huh. Oh, okay. Let's try something here. That didn't seem to work very well. Oh, did you see what happened? That was pretty cool. Reset. Okay, so I started with this, and I ended up with a 2-cycle. So it's 2 cycling that's oscillating right there. Actually, let me see some. Let's reset this. Let's do let's see, what if I extend this out a little? It's symmetric though. Is that right? 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. Wait a minute, something. Oh, it's not oscillating. It stopped oscillating. Let's fill this square in and see what happens. My bird's finally eating food. Oh, I did something wrong. Whoa. I did something wrong when I built this. It's not quite symmetrical. It's a little bit off symmetry. Oh, it ended up into a two cycle. It just destroyed everything. Let's see. What did I do wrong here? Like this? right. It's supposed to go. I don't even know what I'm doing. It should be a square on the end of that point. There we go. Like this? No. Math and computer science and stuff, it's kind of my forte, but that's all symmetric. Okay, that was weird. It just exploded. Didn't like that for some reason. Let's take this off. It's getting worse. It seems like it's getting worse. I think we have to be small here. That's what I started out with. Let's try something like this. My bird, you're really funny. I can't get it to go into. I want to get it to go into chaos, but it's ending up in like a 4 cycle here. Maybe it's because of this design. Let's try something a little more complex here. Well, that just killed itself. My bird's like, okay. I'm starting to feel like symmetry is important. Okay, that's oscillating. Oh, yeah. So if let's see what this does. Oh, yeah. Oh, I did it. Oh, shit, I did it. Oh my God, I fucking did it. Okay, how I did this. All right, so there's what I did was, I did this here, and then I watched at the end of this run, I got these lines here. So they're like repeating each other. So what I did was I filled in the spaces of those 3 lines going across, and I kept my eye on it. Oh, it's a little bit off. We'll see what happens here. Try 0, 0, x, x, 0, 0, then under that x, 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 0, 0, then under that. The zeros are all filled with, oh, you're talking. XX, 0, 0, XX, and then you've got X, 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 0, X, X. X, 0, X, X, so you got X, 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 4, no. You got 2 zeros and 2 X's. I started with the 2 X's. And then under that, 3 X's, 0 and an X. 0, 0, X, X, 0, 0, 0 is square, square, space, space. Oh. Oh, so. Wait, let me do it on the same line. Square, square. X, 0. The zeros are the filled in bits. Three zeros, and then you've got 3 zeros. Oops, wait a minute. No, I did that wrong. The zeros are the filled in. It should be like this. And then X, O, X. Wait, X. So this is X, O, like that. Uh-oh. I gotta admit, mine looks, mine looks pretty, but we're gonna have an attack here. Yours attacked mine. Hate to say it, but I think mine looks prettier. But yours is interesting. It moved out though. It sent something away. I want to see what happens to mine if it doesn't get attacked here, because mine was doing something interesting. I wonder how far. I think I've done something here. I don't know if it's chaos yet or not. Doesn't look like chaos because there's patterns. Uh-oh, it's cycled down. It's cycled down to that. I got a lot further though. Yeah, that's interesting. Yours is pretty cool. I guess it sent out stuff, huh? What if I put... What if I... Too bad I couldn't do a mirror image of this. If I had this in the middle... Wait, this would be... How the heck would I do that? It's open here. Strange. Well, that was interesting. The game of life. I'm just wondering about dimensions and stuff like that, and going back to this other stuff that I was trying to figure out. I got a little bit lost. But that's interesting, though. I'll have to check out some of these programs. Yeah, then I was just going to go into like the coordinate system, and I was going to talk about how to draw pictures on, like, if you have a real data set, you take the real numbers and you convert those to numbers that you can put on a computer. In other words, I noticed that, like, if you use digital ones and zeros, I suppose that's okay, but first of all, your computer has pixels, and those are large numbers. So those are screen coordinates. So then you go from your real coordinate system to, I don't know if it's called homogeneous or whatever, but you go from the real to the 0 and the 1, and then you go from there to, I think you have to rotate. You've got to rotate it such that it matches the computer program that you're writing. Instead of going from the upper left-hand corner down, you want to go from the lower left-hand corner up. And then you got to translate. You got to move that all over so that the origin's in the middle. And then once all that's done, then you convert those numbers to pixels. I guess you could do it that way. Because I saw one programmer, he was programming the chaos equations with floating numbers, and that would, to me, that would be, there's more efficient ways of programming this stuff, and I don't know, I'm just kind of investigating. Yeah, something like that. I don't know what else, there was something else I was going to look at, but I don't know. I think that's it, really. Oh, here? Did I go over this? I think I did.
6494, 0.565, 0.565.
So this is where this guy is.
0.56522, 0.56522.
Let's see.
0.56522, 0.56522. Okay, you know what's going to happen. It looks like, actually, and this is believable, right? Sometimes populations stabilize. And this is good because this is the real world being described by a simple equation. This is not all that exciting, I have to say, but at least I can do this calculation repeatedly. I can bash the button as many times as I like, and it's not changing anymore. It's genuinely doing the calculation, but it's giving the same answer. It's what they call fixed
this is
point
that
for iteration.
Feigenbaum
So the rabbits
constant.
are
I guess I
breeding,
already went
but
over
they're
this.
also dying, and they're dying and breeding
Trying to
at the same
figure
rate, and
out
something's balanced.
some of these numbers. I want to type something in and just kind of get into a little bit more of why I'm doing this. Let's see if we can look at some of these actual images. See if we can find some good ones here. Here's a good one. Well, I don't know about the music. I'm not playing the music because... So, these are strange attractors, like that one, I guess pretty cool. They all have these letters that are associated with them. They're like 10 or 15 or 20 characters long. And you can see they're three-dimensional. And what I'd like to do is I'd like to be able to write a program that plots the individual phase space, like the x and the y, the x and t, the y and t, and that sort of thing, and set that up as a hologram. That's that's part of my journey. But the other part of the journey is trying to figure out this dimension, and maybe the Lyapunov exponent has something to do with it. I don't know. I have to look into it some more. These are strange attractors. They're pictures of what is considered random noise, but they have certain designs to them, and I'm wanting to build electronic circuits that mimic these types of filters so that I can actually create a filter like this to process noise and see what that does to noise, how it filters out the noise. It would be interesting to hear what it sounds like. I don't think anybody's ever. I wonder if I could. Let's see, strange attractor noise. I wonder if that's in here. I wonder if anybody's messed with that. Strange attractor with added noise. Use strange attractors to generate sound. A lot of this stuff, I mean, it's not real. People are doing things with this that are not like how I would make the sound I used to program a long time ago. Built a 2D RPG. Oh, that's pretty cool. Yeah, I program in Visual Basic with, I use C+ to do the repetitive math stuff, and then Visual Basic to write the program. Let's see what this is here. Yeah, I use GW Basic. That's what I started out with. I was on a Commodore. I hate to say this, but that sounds very familiar. It sounds like something I've heard before. And I don't think it's related to this video. I don't know. Yeah, that just doesn't sound right. Yeah, it's definitely not in sync with the video. Noise point cloud. What is this? Noise point cloud fed into Lorenz Attractor. Who cares about topology? I'm looking at some of this other stuff here. My bird is... Wow. Okay, let's see. How come I can't find anything else here? What's this?
Hi, welcome to an early beta.
Oh my god, this guy's mic is distorted.
The whole idea is to show strange attractors both in a dynamic way as opposed to in still pictures, and also to play the sounds that they generate. So what you see on the screen here is a strange attractor I call Bainbridge, after an old professor of mine. And it's got two parameters, A and B, that can be controlled here. And we start off with no sound playing. The volume is 0. That's in case your speakers are already turned up high or you've got headphones on, so you can nudge up the volume gently. I'm going to raise it up using the spinner control
mic is severely
to
distorted.
something like 0.15.
I'm a musician. I got a studio.
Typically 0.1 to 0.2 should be good enough. And what you should be hearing now is a pretty high tone. Now, the attractor right now is this kinky little curve. However, if I change the A parameter, that curve will change.
I can't hear the noise at all.
So you can see
over
this
his microphone.
dynamic system. They split again into 60. of the system at any given time, so it's not really as dense as some of the pictures you might be used to seeing of strange attractors.
Sorry about that. Now I don't know what this is. Someone's actually built a device that has a picture of attractors on. I saw this a while ago. Demo of a dual oscillator that is frequency modulated by a Lorenz Attractor. I doubt that very seriously. I saw this before. I wasn't very impressed. I don't remember, actually. Yeah, I don't think that's... It's hard to tell. It looks like it's synced, but there's not a lot of projected on 2 dimensions. There's not a lot of frequency variation in this rig. It all seems to be, well, I don't know, maybe it's just me. I guess you can adjust stuff with that. I don't know. Who knows? What's this one here? Driven by Bach. What's this? Yeah, I don't think so. Well, anyway, what else is on here? Is there anything? I don't think there's anything in here. Stage light sounds. I've been wanting to do music and sound together. And I want to incorporate, well, okay. That's just advertising something. Anyway, what else have I got on here? Well, I sort of went over logarithms. I sort of went over the dimensions. I have to come up with a program for my stream that actually gets into the programming of the attractor and the pictures of them. This is interesting though. I mean, I don't know if you could do this to music. I'm thinking in terms of 3 dimensions. So like the further away a sound is going to be, it's going to be quieter. You know, things like that. I don't know. There's ways to do it, you know, programming pictures to sound and everything like that. I don't see a lot of it on here, especially with these fractals. But anyway, that's sort of my stream. I'm probably gonna I didn't really do as well as I had intended for the idea of the stream. I wanted to relate like the dimensions of a plane and a cube, and I wanted to relate those dimensions to the dimensions of attractors or chaos theory. And it seems like they're calling those dimensions, they're not, it doesn't seem like they're the same, but when you look at that Sipinski triangle and you see that there's less area, and that number, that dimension gets higher, that dimension is related to that. Let me try something here. Let me just, well, I got dimension. Triangle dimensions, I don't want that. The Hausdorff dimension, what's this? We'll have to, we'll play a, we'll look at a wonderful ad here. Well, actually we won't because I don't have it on there. Hang on just a second here. Here. Oh God, he's writing this.
Square and scale it up by 2, you get 4 copies of the original square inside the larger square. When you scale by a factor, the number of copies of the object is the scale factor to the dimension of your set. We'll make dimension a bit more formal in a minute, but the scaling property of sets is intimately related to our colloquial intuition for the dimension of a set or shape. So how do fractals scale? We're going to consider this one. It's called Sierpinski's Triangle, or the Inception Triforce, as I've heard it called. It's an equilateral triangle, but then you remove the middle equilateral triangle, and then you do the exact same thing with the 3 equilateral triangles left over, and then repeat that with the triangles left over, and continue forever. And what you get when you're done with doing that infinitely many times, that's Sierpinski's triangle. When you scale this triangle by a factor of 2, you get 3 copies of it. So what's its dimension? Mathematicians would be careful and specify what kind of dimension we were talking about, but it just so happens that this intuitive version of dimension falls in line with what is called the Hausdorff dimension of a set. However, the Hausdorff dimension of a set is a bit more general and can be any number greater than or equal to 0, which is a bit mind-boggling. To start to understand this a bit more, let's look at a curve and call it C. If I were to just measure C with points, there would be infinitely many of them, which isn't super satisfying. And if we tried to measure it with another line, then we would have something akin to its length. However, if I tried again to measure it with anything higher dimensional than a line, like squares, I would have 0 squares in my line. When we take the Hausdorff dimension of a set, we're essentially doing what we just did with the curve C, but on a larger scale. That is, we'd measure the set with objects of all possible dimensions, and then the one that works the best tells us the dimension of the set in question. Notice that was essentially what we did with the curve. We can graph the measure of the curve as a function of what dimension we are using to measure it. Anything lower dimensional than a line or dimension less than 1 would be too small in a sense to measure the curve, so those measures are all infinity. But anything higher dimensional or dimension greater than 1 used to measure the curve would be too big in some sense, so those measures are all 0. This tells us that lines are the jump point, and therefore the curve is one-dimensional. When we use lines, we get something akin to length, which is non-zero and not infinity either. Sets like this that have a jump point where this way of measurement is not 0 or infinity are super nice, as they make the determination of dimension, which, if we are being completely rigorous, can be very, very involved, a bit easier. We call these sets S sets, and they will be useful in about a minute. But that was a lot, so let's recap. Hausdorff dimension works exactly the way you want it to, and we saw this was the case for a curve. But we also said that the Hausdorff dimension does not need to have a whole number as its value. So what does a non-whole number dimensional set look like? There's no intuitive object that we can use to measure a set that has dimension 0.5 or some other non-integer number, but there are sets that do have such a dimension. And in fact, according to the Hausdorff dimension theorem, for every positive real number s, there are infinitely many sets that have that dimension s. Many of these sets are fractals, so let's go back to the only fractal we have gone over so far, Sierpinski's triangle. After removing triangle after triangle, it appears that there isn't much left on the inside of the original triangle. So what would you actually use to measure it, to determine its dimension? That would be pretty hard to come up with. So we're going to abstract the problem into a computation. Let's say that the correct object to measure this set with has dimension s. Sierpinski's triangle also has a property called self-similarity. That is, whenever you scale up the triangle, you get more detail in the triangle. So we should try arguing by talking about its properties of scaling. Consider these three smaller triangles in the Sierpinski's triangle. Notice that if I measure all three of them, I have actually measured the entire Sierpinski's triangle. So if I add together these measures, I get the measure of the whole thing. Next, notice that if I scale each of the smaller triangles up by a factor of 2, I get the entire triangle. And like with the line and the box at the beginning, the measure of the scaling is given by the factor I scaled by to the dimension, which we said is s here. So each of the measures of these three smaller triangles is 1/2 to the s times the measure of the entire Sierpinski's triangle. In other words, we can get a smaller triangle by scaling the entire Sierpinski's triangle by half. Now we run into a little issue. If s is the jump value and the measure here is infinity or 0, then we can't divide by the measure's value, so we can't solve for s. However, we get really lucky. Although we won't prove it, Sierpinski's triangle is an S set, which we talked about briefly before. It just means that at the jump point that we're worried about for this set, we don't get infinity or 0 when we measure it. The rest is just a little bit of algebra, and we find the dimension of Sierpinski's triangle is log 3 over log 2, which is definitely not a whole number.
I wonder, he's saying that he comes up with this 1/2 figure when the other video was using 3/4 of a figure. So I don't know what this person's doing as far as coming up with this set theorem. S is supposedly the dimension number, but I don't know where he came up with this 1/2. That's confusing. Let's see what he's got to say here.
Anyway, I know I said I wasn't going to post a video this week, but it just ended up working out that I could post one, and I know it's late, but I'm giving myself a break on it being late because I still posted one this week. So anyway, I hope you enjoyed this video. If you want to see more videos like this, you can give it a thumbs up and subscribe for more videos each week. There's also a poll you can take, and that tells me kind of like what general subject area you guys want to hear about. So
more on the Sipinski Triangle. In other words, how to come up with. There's a square one. What was that called? Crap, I can't remember now. Let me just write this down here. There's this. Wait, that should be in Wiki. I wonder if it's in here. Wait a minute. It was the one with the squares. Yeah. It could have been. Well, a level 5 approximation to a Sipinski triangle obtained by shading the first 2 to the 5th 32 levels of a Pascal's triangle. If the binomial coefficient is even or black otherwise. Hausdorff dimension. as a measure of roughness, or more specifically, fractal dimension. For instance, the Hausdorff dimension of a single point is 0, a line segment is 1, a square is 2, a cube is 3. So according to this definition, it's using those numbers as a means of relating what we normally think of in dimension to fractal dimensions. So here it is, right in black and white and blue. Whereas before they were talking about self-similarity and how that dimension relates to a similar similar producing objects. I mean, just because it says that, it doesn't mean that a fractal dimension is a real thing. Like, a piece of paper exists in a plane of space. So if you take a paper and you take pictures of it over time, you're looking at a projected image of something that's three-dimensional, but the real object was two-dimensional. So if you take a cube, which is real, we can see it, we can hold it, and you move the cube over time, what you come up with is supposedly, it's called a hypercube. I'm gonna just take a look at this here. This is supposedly a fourth-dimensional object. And you can take matrices, and just you can add bunches of numbers and matrices and create a dimension that way. But I'm thinking in terms of there's got to be something in existence that is not related to space and it's not related to time, but it would have to be related to something. And the only thing normal people can relate to is something that's in our own physical universe. An animation showing how to create a tesseract from a point. An n-dimensional analog of a square and a cube. My bird's like, uh-huh. Oops, it says Petrie polygon orthographic projections. I should save this page because I want to know, there's different types of projections that you can do on a flat surface to see what they look like. 13 cube, 14 cube, 15 cube. My bird's like, uh-huh, uh-huh. All right, so I'm going to ask a question here. Let's ask a question. Let's ask, let's see. Dimensions after the third. A universe of 10 dimensions, physics.org. What are the first, second, third, and fourth, and fifth dimensions? Some people say that maybe space is or time is the fourth dimension, and space is the fifth dimension. You know, I don't know. Who knows these things? Scientists believe there may be many more. In fact, there's probably an infinite number of more. I put down on my stream I wanted to talk about infinities. And I didn't get to that point. But there's like, most people think of infinity as being a number that gets, the numbers keep getting bigger and bigger or smaller and smaller. Like you can go from 0 and just add numbers and it goes off into infinity. That's one form of infinity. Another form of infinity is that if you take a line and you cut it in half each time, you can never reach the end of it. That would be another form of infinity. You could take a number like pi and it just goes on and on forever. There's another form of infinity. There's many different types of infinities, which I didn't even think about when, years ago when I was thinking about all this stuff. But I think it's important. It's all of this is an important aspect when you're thinking of dimensions and how things can exist in different states, I guess. Of course, I'm not telling anybody that I'm talking about time travel or anything like that. Okay, so here we go. It says, the third dimension involves depth, the z-axis. Scientists believe the fourth dimension is time, which governs the property of all known matter at any given point. Let's see. Plotting its position in the universe, etc., etc., etc. The other dimensions are where the deeper possibilities come into play. And this is where things get tricky. According to superstring theory, the fifth and sixth dimensions are where the notion of possible worlds arises. If we could see on through the fifth dimension, we would see a world slightly different from our own. In theory, if you could master the fifth and sixth dimension, you could travel back in time or go to different futures. Yep, my bird agrees. This is on phys.org. Okay, I just read about this brain thing. Corresponding to a brain on which all known particles besides gravity would be restricted. Brain theory. And another parallel universe scientists thought they found that doesn't actually exist. I believe in the possibility of parallel universes. I think it's an interesting concept. But then again, I'm studying fractal dimensions and the possibility of the existence of life between dimensions. My bird says, hello. That's where my mind is. Hi. But anyway, I probably streamed long enough on this subject, almost 3 hours. I was actually going to draw some pictures and stuff. And I had my notebook out looking at some things. But that didn't happen. Let's see, the next time I do a stream like this, I'll have my programming set up. I'll have some programs up somehow. I don't know, it's just strange. How do you figure out, like, if the fourth dimension is time, and you take a three-dimensional object and you move it, there's other things to consider. There's energy. Supposedly there's quantum theory and particles. And since we don't really have the capability of examining particles as a layperson, we have the ability of looking at waves, or we could take pictures, like we could accumulate a bunch of pictures of particles, and those pictures would turn into waves. And an example of that's called the Fourier transform. Let's see here. Let's see, Fourier transform. Slit. I wonder if it shows that. All right, so this is the Fourier. Let's see what we got here. An advertisement about something. Oh, this is a good channel too, by the way.
This right here is what we're going to build to
3
this
blue,
video.
1 brown.
A certain animated approach to thinking about a super important idea from math, the Fourier transform. For anyone unfamiliar with what that is, my #1 goal here is just for the video to be an introduction to that topic.
Wait, didn't I
But
go
even
over
for
this?
those of you
Not
who
here,
are already
but-
familiar with it, I still think that there's something fun and enriching about seeing a graph and a pretty quick winding frequency.
You've got different frequencies coming together, and he separates the frequency, and by looking at the Fourier transform, it shows the harmonics of all the frequencies involved. It just pulls it apart, but that's not what I was looking for. I wonder if the double slit experiment right here. I want to look at this.
Professor Dave here. Let's talk about the double slit experiment.
He knows a lot about the science.
Yeah, I know.
We understand that both light and matter behave
This is
as
Professor
both
Dave.
particles
I've
and
never
waves.
seen this video before.
But we glossed over some of the technical details, so let's zoom in for a moment. In 1801, Thomas Young performed experiments where light was passed through a plane with 2 slits in it, striking a screen beyond. The diffraction and interference patterns that resulted clearly supported the wave model of light, with the brighter bands representing constructive interference and the darker bands representing destructive interference, with the width of the bands being a function of the frequency of the light. Later in the century, Maxwell showed that light is a wave of oscillating electric and magnetic fields. So it seemed as though the case was closed on the declaration of light as waves. But as we said, in 1905, Einstein solved the problem of the photoelectric effect by assigning particle nature to light. Thus, wave-particle duality was born. Later, de Broglie proposed that particles must therefore also display wave-like behavior, and this was shown to be true in an experiment, just like Young's more than 100 years prior. This modern version is what we are typically referring to when we talk about the double slit experiment. From this, it was shown that a beam of electrons exhibits diffraction and interference patterns, just like light does. This demonstrates the wave-like properties of electrons, and by extension, matter in general. Later, low-intensity experiments showed that even an individual electron, when passing through biprisms or slits, will interfere with itself, making the wave-like nature of the electron undeniable. So it was shown that electrons act as both particles and waves. But not just electrons. Neutrons were also shown to exhibit diffraction patterns. It must be understood that since all particles are also waves, literally any object could hypothetically exhibit a diffraction pattern, so long as the object passes through an aperture roughly the size of the object's wavelength. But remember that massive objects have incredibly tiny wavelengths, so for something like a human being to diffract, they would have to pass through an aperture around 10 to the negative 36 meters wide, which is a trillionth of a trillionth of a trillionth of a meter. So this will be pretty tough no matter how much you diet. In this way, we begin to see how Newtonian mechanics is not the fundamental descriptor of motion, but rather that it emerges from quantum mechanics as objects become large enough that their wavelengths are negligible. So don't worry, everything you learned in classical physics will still work just fine for any object you can see with your eyes. But along with these waves of matter came the wave function and the quest to describe it mathematically. This would be impossible without the creation of quantum mechanics, which was achieved by a host of brilliant minds. But we will focus on two people in particular, Erwin Schrödinger and Werner Heisenberg.
Einstein's in
Let's
the middle
move
right
forward
there.
and see what they had to say.
Let's
on the
just
subject.
forget about Einstein.
Thanks for
He was
watching,
my
guys.
mentor.
Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Uh-huh. Well, that was interesting. I wonder what my IQ is. USA's most important accurate test online. Take the IQ test. Good luck. You have 20 minutes. Choose the appropriate shape A and replace the shape that's missing. What the hell? I got 1 minute to do each question. Choose the appropriate shape and replace the shape that's missing. Oh, wait. Oh, wait a minute. Wouldn't it be? Yeah, here. Choose the appropriate shape and replace the shape that's missing. That's strange. I don't know. I just guess that one. The shape that's missing. Well, it depends on which direction you go, and that's too ambiguous. Oh, I see what's happening here. It's a different rule set. These are rule sets. What the hell is this? Just based on the number of items? Oh, okay, okay. I got this one. Wait a minute, where the hell is it? It's not there. Either is. Oh, it's there. Okay, wait a minute. There it is. Oh, do I have 15? Oh, got it. Oh, wait, 15, what? I got 15 questions in 18 minutes? No. It have to be this one, wouldn't it? Oh. Hey, bird. I'm doing an IQ test online. See how smart I am. Hello. Wait a minute, are these? Good Lord, that's a hard one. Holy shit, man. What the hell? What kind of an oddball IQ test is this? I'm just going to guess. 3 triangle. That's got to be easy, wouldn't it? Oh, they're different though. Have to be this one. Oh. What? Oh, it's a pattern. Have to be this one. 2, 1, 2. Oh, well, I got one of those. Those are the same. Apart, opposite, apart, opposite, apart, opposite. It's got to be this one. 38, 37, 35. Oh. 17, 10. 38, 37, 35, 32, 32, 3, 1, 7, 1, 2, 2, 7, 8, 8, 8, 2, 7, 7, 8, 0. Fuck, I don't know. 1. It's got to be 1 something. It's got to be 1, 8. This is 4, 5, 7, 11, 1. Good Lord. I don't know what this one would be. Wait, 3. I guess that one. Circle, square, triangle. Triangle. Good Lord Almighty. Wait, it's got to be either one of those two. Square, circle, it's got to be this one. Single wavies, double wavies, triple wavies. It's a triple. That one's apart. Those are facing each other. That must be down. There's one missing. Yeah. They are repeating each other. 1, 2. 1, 2. 2 of each. 2 of each. 2 of each. One's missing. Fuck. How much time I got? 13 minutes. One of them's missing. I think it's... No, it's going to be this one. I got 15 minutes to do 5 questions. Singles. It's got to be... Singles, doubles, triples. One of those 3. Right, up and over. Over, over, right. Right, right. It's not down. I think it's this one. Is this an IQ test? Brain Metrics Initiative? What the hell kind of an IQ test is this? Like, what's the where's the question capital of France? I mean, really? Alright, so you got 2, 2. Wait, 2, 2, 2. 2, 2, 2, 2. Wait. Opposite? Opposite, opposite, opposite. It's got to be same, same, same. It's not there. fuck? Opposite, opposite, opposite. Same. Oh, wait, that's down. Wait a minute. Wait, it's gotta be... No, it can't be that. It's gotta be 2 in the corner. It's gotta be this one. 1125. I had to take similar tests like this when you go into the military. They give you shit tests like this. 147, 10, 13, 16, 19, 22. Add 3, 25. Add 3, 25. Line, square, line. Oh, it's got to be this way. Single, double, triple. Right, left, right. Single, double, triple, right, left, right. It's got to be line, triple. It's got to be this one. And I got 10 minutes to do the last one. I might as well think on this one, huh? We got 1, 1, 1, 2, 2, 2, 3, 3, 3. Over, under. I got that one. That's easy. Oh, wait. Yeah, that's easy. It's right there. I think I missed 5 of them. I'm gonna say good. I'll see. So if I missed 5 out of 20, let's see. Wait, 75. I think I did better than 75%. Oh, good. You completed the test in 10 minutes and 15 seconds. That's faster than 77% of people tested. Your strongest category is visual perception, where you scored higher than 94% of people tested. Please follow the steps to get your IQ score, your personal BMI IQ certificate, and BMI performance report. It only costs $20. Order your details now. Instantly worth it. Hey, if I scored 94% higher than people tested, then I don't need to know my score because I already know it. I gotta have something to eat. I've been streaming too long. Oh, 25% off. Get a good deal. I think I had a good deal watching Professor Dave here. Oh, was that even? Yeah, anyway. So the whole idea is trying to figure out, according to the Hausdorff dimension, there is a possibility that fractal dimensions equate with fractional dimensions, according to the Hausdorff dimension theory. If that's the case, then I say there's a possibility of the existence of life between dimensions. And on that note, with an IQ of 94% scoring better than most people on visual perception, I'm going to end my stream and thank you for watching.